What role does the motor cortex play in ECoG BCI control? Imagine being able to control a robotic arm just by thinking about moving your own hand. This is what some brain-computer interface systems aim to do, and the motor cortex is at the heart of this process. When we talk about electrocorticographic or ECoG brain-computer interfaces, we are referring to systems that record brain activity directly from the surface of the brain. This method provides clearer signals than traditional electroencephalography, making it ideal for precise control tasks. The motor cortex is a key player because it is the part of the brain responsible for planning and executing voluntary movements. When someone thinks about moving their hand or leg, the motor cortex generates specific electrical signals. These signals can be captured by ECoG electrodes placed on the brain's surface. Once recorded, these signals are processed and translated into commands for external devices like prosthetic limbs or computer cursors. The process involves training the brain to produce distinct activity patterns that correspond to different actions. For example, thinking about moving the right hand might produce a different pattern than thinking about moving the left hand. Over time, the brain learns to produce these signals more reliably, allowing smoother control of devices. The motor cortex does not work alone in this process. It interacts with other brain areas involved in planning and decision-making, such as the premotor cortex and the posterior parietal cortex. These regions help with spatial awareness and movement planning, making control more natural. As users become more skilled at controlling the BCI, activity in these broader networks can decrease, indicating that control is becoming more automatic. The practical use of this technology is promising for people with paralysis or motor impairments. It can help them operate prosthetic limbs or communicate more easily. The motor cortex provides the neural signals needed for precise, voluntary control, making it essential for the success of ECoG-based brain-computer interfaces. This connection between the brain and external devices is opening new doors for restoring movement and independence. In the field of neurotechnology, understanding how the motor cortex contributes to BCI control is vital. It helps us develop smarter, more responsive devices that can interpret brain signals accurately. This knowledge also guides improvements in electrode placement, signal processing, and training protocols, all aimed at making these systems more effective and accessible.